Okay, so let's move to the first question, which says that the dash discontinuity separates a crust composed of low density silicates, rich aluminium and potassium from the mantle composed of silicates of higher density which contain more magnesium and iron. So during the last week we have discussed about the crust or the earth's internal structure. So where we have discussed that the crust mainly composed of silicates that are rich in aluminium, and in short we called it as let me write it, Cl. Cl represent Si for silicates and Al for aluminium. So this is the major composition of the crust, and we also know that crust are of two types. During that course also you have understood so far that we have mainly continental crust and other one is oceanic crust. And out of these crust we have a more denser oceanic crust because it has a composition of silicates plus magnesium plus some felsic rock as well. That's why we called it as a I forgot the name, mafic rocks. Okay, and on contrary to continental crust, we have a lesser density as compared to oceanic, because here the material composition is mainly of lighter elements, that is silica plus aluminium plus magnesium. So that's why we generally face the density contrast between oceanic and continental crust. Now the question is saying that we need to tell the discontinuity. But the first question comes that what is this discontinuities and how they generate. So whenever there is a difference in composition which can attributed due to the difference in density or phase change, we encounter these kind of discontinuities. And if we look into the Earth's internal structure, there are lots of discontinuity. Why there is discontinuity? Because there is variation between the density and the phase changes. Okay, so let's understand what kind of discontinuities Earth has. So this is the image. So where we can see that first layer of the Earth internal structure consists of crust. Then we have a mantle, and under the mantle we have a two kind of segregation that we called as a upper mantle, and the other one is a lower mantle. So this whole area is for complete mantle. And for the core part also we have a two kind of segregation. First one is the outer core and second one is the inner core. So the first discontinuity that we encounter is the Conard discontinuity that we generally face between the lower and the upper crust. So as in this figure you can see, under the crust also we have a two segregation, and that is due to the upper crust is mainly composed of Cl, that is silicates plus aluminium, and the lower crust is mainly composed of Sima, which is silicates plus magnesium. So this is the first discontinuity that we encounter. There is the second discontinuity called as Mohorovic discontinuity. This continuity exists between the crust and the mantle. Now again, since there is a density contrast between the crust and the mantle, and why there is a density contrast? Due to the composition of the material. So we again face the discontinuity, and here what happens that the depth of this discontinuity is varies. Why it varies? Because the depth of the continental crust that we discussed in the previous lecture, that is more than as compared to the oceanic crust. So in general, the depth of the continental crust is around 35 kilometers, and for the oceanic crust the depth is 8 kilometers. So due to this density variation, we see the variation in the velocity. Now we generally see the variation of P wave velocity, which changes from 6 to 8 kilometers per second. So there is a Morovic discontinuity. Moving to the more deeper structure, we have a Ripeti discontinuity that exists between the upper and the lower mantle. Now the major discontinuity that is very prominent is the Gutenberg discontinuity, because here we see a very nice contrast. And how we see that this contrast? Before answering that, first understand where this discontinuity exists. So it exists between the lower mantle and the outer core. So here is the location of this discontinuity. So here what happens, the P wave velocity suddenly drop and the S wave velocity gets disappear. And I hope you all are aware about the velocity concept, like what is P wave and S wave velocity. And if not, then we will discuss it in a brief. And if you want to discuss it more, then in the next lecture I can prepare a separate slide for the velocities. So the question, okay, now moving to the forward, the last discontinuity that we have is a Lehmann discontinuity that exists between the outer and the inner core. And here what happens, there is an abrupt increase in P wave velocity and the S wave velocity. Now let me ask you one question, why there is an abrupt increase in this P wave and S wave velocity, and why in the upper discontinuity, that is a Gutenberg discontinuity, the S wave suddenly disappears? So can you answer? And if not, that's fine, so that we can discuss this concept, because it is a very important concept. So I want all of you to understand it with a good level. So can you suggest that why S wave velocity decrease, or why P wave velocity, S wave velocity disappear and P wave velocity decreases? Okay, no problem. So the answer of this question is that I mentioned that Gutenberg discontinuity exists between the lower mantle and the outer core, and this outer core is liquid in nature. So the phase of this outer core is liquid, and above this mantle, the lower mantle is in solid state. Okay, now so there is a change in density. Definitely there will be a change in density, as well as there would be a change in elastic parameters. Now what are these elastic parameters? To understand that, let's move to a little bit about the velocity relation. So this is the P wave velocity relation, and the below one is for the S wave velocity, and this relation is for the ideal condition, that is isotropic medium, homogeneous and isotropic medium. Here mu represent the shear modulus, and K represent bulk modulus. Okay, and rho represent the density. So if we talk about the shear wave, what we can see, that it is a function of shear modulus divided by density. Now shear modulus is solid, what we generally consider? We generally consider it equals to 0. Why equals to 0? So if we go into more basic, so what shear modulus represent? Shear modulus represent the resistance towards the shear force or the shear stress. And we all know that fluid can't resist the shear stress because it will flow, and due to which if I write the formula, so if mu equals to shear stress divided by shear strain. So what I said, like if we apply a shear stress on a fluid, it will definitely flow. So it can't resist this stress, and due to this stress, what will happen, there will be a strain because now the shape of the fluid is changing, and this change is so much large that we consider it that shear strain is almost equals to infinity. And if you divide anything by infinity, it would come as a zero. So that's why for the case of fluid, and here the fluid can be liquid and the gas. So in case of fluid, we will get the mu value equals to 0. So now since mu is equals to 0, that's why Vs would also be equals to 0. I hope so far everything is clear. So that's why for this Gutenberg discontinuity, this S wave suddenly disappears because it encounters the liquid phase in the outer core, and the P wave velocity decreases again due to the same reason. So now mu is equals to 0, so there is only one factor that is governing the P wave velocity, that is the bulk modulus. So that's why the P wave velocity decreases. And in this table, here is a general velocity range for each and every material. So you can see that for the air, we have a 0 shear wave velocity. For water also we have a 0. For petroleum, since it is in a liquid phase, so again we get 0 velocity. And if you compare the velocity for the same material, if I talk about the basalt, so the velocity for P wave is almost 6400 meter per second, and for the S wave is 3200. So always remember that velocity of P wave always be greater than velocity of S wave. And why it is so? Because of this extra bulk modulus factor that is getting added into the P wave velocity. I hope the velocity concept is clear to all of you, and why I explained it this. So to understand the behavior of this velocity, and again there is a more important concept that due to this velocity mapping only, scientists were able to map the solid earth structure. So that's why this velocity brings a very like it's very informative to understand the material property. So I hope now all of you can answer this question. So in this question they are asking what is the boundary between the mantle that is composed of magnesium and iron and the crust. So if we again go back to this diagram, so between the crust and the upper mantle we got this Mohovic discontinuity. Moving to the next question. Now they are asking that what type of force is responsible for the movement of rigid lithospheric plate over the partially molten asthenosphere. So all these terminology like what is a lithosphere, what is the asthenosphere, we have already covered in our first week session. So Akshay, I hope you are aware about these terminologies. So are you aware about these terminologies? For example, this lithospheric, asthenospheric. Okay. Okay, no issues. So actually we discussed this thing in the first week session. So I think think I'll have a time. So even after discussing this week 2, we can go back to the week 1, and I can explain you the the content that I have showed in the week 1. Yeah. So okay. So I hope you are getting every, like, the things that I have explained so far. I'm getting okay. Okay. So yes, so we want to, so just a brief, that lithosphere is a rigid plate, like, since we have a plate tectonics activity in within the earth. So the plate is consist of this lithospheric, that is a rigid solid slab, you can consider it as, and asthenosphere present just below the lithosphere, because to make this movement happen, you need to some, like like liquid material, so that plate can float over it, otherwise the motion would be very difficult. So this asthenosphere is in the liquid phase, and this lithospheric, that we call as a tectonic plate as plate, it is a rigid part or the solid part. Okay, so if I have to explain simple diagram of a slab, so this would be my lithosphere, and under that, suppose like wooden block is floating over the water. So this is a, I think, very simple explanation of this concept. So this water would be my asthenosphere. Okay, so now what they are asking in this question, that what type of force is responsible for the movement of rigid lithospheric plate over the partially molten. So from here also you can understand that it is in the partial molten state, that is asthenosphere. So the options that we have for this question is gravitational force of earth and moon, magnetic force of the earth, mental convection system, or all of the above. So if we go one by one, so gravitational force for earth and moon, do you think that it can play some role into that? Yes. So yeah, it would make it. So if we go to the second option, that we have magnetic force of the earth. Magnetic force, I don't think again it will act as a driving force, because here we are talking about a closed system where two entities are existing. So magnetic force, don't think. And what about the mental convection system, or all of the above? So now we are left with two options. So before rejecting or accepting this third option, we first understand what is this mental convection system, because we all are aware about the gravitational force and magnetic force, but this mental convection system is bit like related to completely a science part. So let's understand what is this system. So from this simple illustration, so it's like heating a water, because now we are talking about the convection currents. So convection currents happen when we boil a water. So suppose we are boiling a water, and due to which only the water gets hot and hot with the time. And this we have studied in the physics, that this convection current exists in a loop form. So here you can see there are two loops that are maintaining, because there is a continuous flow of the heat, and due to which the upper water is getting warm. So the similar phenomena happens within the earth as well. Now since our core, which is the outer core, that is in the liquid phase. So this liquid core acts as the main source. So this liquid core, what does, it heats the mantle, and this mantle heats the plates. Now heating the plate, it creates convection cells due to which these plates move, and this plate is the lithosphere or lithospheric. So that's why we got this plate movement. So the main driving force for moving these plate is the convection current that happens within the mantle, and the source of these convection current is the outer core that is in a hot state, and since it's in a liquid state, so that's why it can transfer the heat. So I think now you can answer this question very well. Again, so to give the exact scenario of the earth, we can see that we have an inner core and then we have an outer core, and here if I would like to a scale of depth, so here the depth is I would say, no, it would be in the reverse direction, because so the direction of depth would be this way. So here is the top surface, and here we are at a core which is around 6,371 kilometers. So at the mantle part, you can see there is a mantle convection cell that is forming due to getting heat from the core. So it is acting like outer core is acting as a stove. If I take the inference from the example that I have given earlier, and due to which these plate or the lithospheric slab are moving, and due to this movement that we called as a plate tectonics, we see the different kind of landform on the surface. For example, trenches, ridges, or mountain forming or volcanic chains. So these are the outcomes of this plate movement. And what are these landforms? Again, we have discussed in the last session. So I think it's clear still now. So moving to the third question, that is, if I read out, is according to the theory of dash, low density rock blocks float high and have a deep roots, whereas high density blocks float low and have a shallow roots. So since Akshay, you are the only one present, so I'll ask from you. What do you think that will the plate tectonics would be responsible? Okay. Okay. I have no idea. Okay, no, but I hope so far you have understood the things, and you have no doubts. If you have, then you can ask it right away and try to answer that. But you aware about the plate tectonics, like in like bits and pieces, you are at least familiar what it is. Okay. Okay, nice. And the second option that we have for this question is the seafloor spreading. So seafloor spreading, if I would have to explain, so here you can see when this convection cell are diverging. So since the force makes the plate to diverge, so definitely the plates will diverge from here. So that would be the boundary of the divergence. So at this divergence, what landform we receive is the ridges, and due to these ridges we also called it as a seafloor spreading. So as its name suggests, that seafloor is spreading because it is diverging. Now plates is diverging, and this hot mantle will come to the surface and will form the new plates. So that phenomena we called it as a seafloor spreading. But since we are talking about the deeper roots, so definitely the seafloor spreading would not be the wise choice, because this happens when we talk about the plate level, that is the lithospheric level. Now the third question that we have is the isostasy. Now this concept is important to understand, because it would be, I think, useful for you to answer questions for the exams as well. So let's move to this isostasy concept, and this is a bit not bit, I think I would try to explain you in a very simpler form so that all of you can understand. So in this isostasy there are lots of theory about it. So let's talk about the first researchers who try to explain the phenomena. But the question comes like, why they conducted this kind of series of experiments, like what was the major motive? So major motive was to understand the mean density of the earth. But you all can say that we have a gravitational formula, and from that we can easily calculate the density of the earth. But by that time, in around 19th century, the g constant that we have, a gravitational constant, was unknown. So by that time no one has identified the value of the g. So that's why these researchers try to find the mean density through some experiments. So what experiments they conducted is a very simple experiment. What they do, they use the deflection of a pendulum. So here in this figure you can see this is a mountain. Okay, so at one end of this mountain, they using the pendulum, they try to see its deflection, that how much is deflecting from its mean position. So the deflection angle they defined using the beta n, and for the to make the standard, they have used two stars position, that is the north and the south. So due to this star position also, we will feel this pendulum will feel the deflection, and this deflection angle definitely would be lower than this deflection angle, because the distance is high as compared to the mountain. So they assume that due to this mountain, the angle subtended would be the beta n, and due to this star, the angle would be the alpha n at the center of the earth, that is at the core. Similarly, for the other end, that is for the south end, they conducted the same they conducted the same experiment due to the pendulum deflection. But what thing that were confusing to them, like if I talk about the Pierre Bouguer, so they assume that since mountain has some mass, like extra mass as compared to the surface, so what they expected, that due to this extra mass the deflection would be high, which is very obvious. But they observed that the deflection was less as compared to the expected one. So now the question comes, why it is less? So to understand this phenomena, there's other researchers who attempted to identify the cause behind it. So comes to the George Everest, who conducted the same experiment. This experiment was conducting in Europe. I forgot the exact location. But this George Everest conducted the same experiment in the foothills of Himalaya. And even he also observed the same thing, that the deflection on the plumb line was not as much as expected. But by the time of 1889, C.N. Newton were able to answer that question. So the answer of that question was, since they were thinking that the density or the mass of the mountain would be equals to the density of the crust. But what they found out later, the density of this mountain material is less as compared to the crust density, and that's why they were getting a less deflection. So to explain this phenomena in more detail, they have proposed two kind of model that we called as a isostasy models. So first one is the Airy model, and he is also one of the scientists that were involved in this isostasy work, and the other is the Pratt model. So first let's understand the Airy model. So in this Airy model, you can see, suppose we have an extra mass in the form of the mountain. So definitely mass is there, so you will feel the different gravitation value as compared to the other area. So this mountain height is h1. Now you have another mountain of which is a lesser height of h2. Now below that the crust thickness would be constant, but what is happening that due to this extra mass at the surface, we will get the extra mass at the mantle as well. And why it is happening? Due to the isostasy. So what is this isostasy exactly? See, every system tries to maintain the equilibrium. So here in the earth, it's tried to maintain the hydrostatic equilibrium, and to maintain that it has to have a extra depth of the crust material only, so they can compensate of this extra mass in the form of mountain that is present on the surface. And this thickness of this extra block would be proportional to the thickness of the mountain. So we can see that since the thickness of this H1 mountain is more as compared to the H2, so that's why this thickness of this block that is just below to this mountain is high as compared to the block that is just below to the this H2 thickness mountain. So this is the first model to show that how Earth maintain this hydrostatic equilibrium using the Airy model. And since now we only talk about the mountain, and similar things happen for the ocean. So now as I mentioned, that oceanic crust has a higher density as compared to the continental crust. And that's why you can ask that why there is no material till this depth. So the reason is, since it has a higher density, so with this depth of mass, it is compensating the hydrostatic equilibrium. And this depth, the sea depth, we called it as a compensation depth. So it's like the same phenomena that we understood in the I think in the chemistry when we studied the equilibrium, like I forgot the exact name, but yeah, equilibrium. There also we always try to balance the both side of the equation. So similar thing is happening in the earth, and this phenomena we called it as a isostasy. And to understand this isostasy, there are many models, but here we are discussing only two very famous models. First is the Airy that we have discussed now, and the Pratt model is the another very famous model. Because why I am discussing only these two models, because generally the questions comes from these two models only. So there are the relation, there are the empirical relation that they have established. So please go through that relation, so that in exams you can solve the questions related to these models. So first you need to understand the model, so that's why we are understanding. I hope you are aware about now all the parameters. So rho C is the crust density, rho M, because since this is the boundary representing the crust and the mantle, so rho M would be the mantle density. And below the mantle we have the compensation depth. So everything, not everything, every mass would be balanced up to this depth, that is the compensation depth. And here D is the like sea floor, not like sea water depth. So the water depth, and because after the water we have the sea floor. So from the sea floor this oceanic crust starts, and below that there is no other material in solid form, because till this depth of mass it is compensated. And now let's move to the another model, that is the Pratt model. So in this Pratt model, so on contrary AE model, where we can see the variation in depth, what they did, they moved the compensation depth. Now here we have a compensation depth below the mantle, but here we are getting the compensation depth at the crust mantle boundary. So that is the one major difference between these two models. So for balancing this, so to maintaining this hydrostatic equilibrium, what it does, it changes the density. So here you can see the region where we have the mountain. So this block that I am highlighting with the green color, you can see here we have a rho 1 density. And for the block where we have another mountain which has the lesser height, we have a rho 2 density. And the place where we don't have any extra mass on the surface, we wait. Okay, so where we don't have the extra mass, we are getting the our expected density, that is density of the crust, which is generally around 2.7 gram per cc. And for the oceanic part, we have a rho naught. So now what they did, they fixed the density. So they assume that where they have the extra mass, the density would be different as compared to the normal density, that is density of the crust. And this density would be proportional again to the height of the mountain. So in summarizing this model, they assume that this is the local isostatic compensation, because here we are considering only crust to mantle system, so that's why it's a local isostatic compensation. And it incorporates that outer layer of the earth rest on the weak magmatic substratum. So that also we can see from this figure. Now from the different expansion, there would be a different vertical column of the density. So that is also evident, and I have just explained. And for the higher the column above the common base, lower the mean density. So that was the phenomena that that we got from this experiment, that this mountain zones, due to this mountain zones, we will get the lesser density or the lesser gravitational pull as compared to the other places, because this consists of lower density materials. So I think this is it from my end. Now you can ask any questions if you have so far from this lecture. But before that, okay, he left. Okay, Akshan, now you are the only one. So again, you can go ahead if you have any questions, and don't think that don't about anything. Just ask if you have any questions. Yeah. Okay. Nice. Mm-hmm. Mm-hmm. And from online video, you meant like from which video? Like the search video. Okay, okay. Yeah. Okay, go ahead, huh? Okay. Mm-hmm. Okay. Okay. Um, so for that, I think if you have this query, then you can post it on the discussion forum of this course. So there the TA will answer your question, and but if you can read out the option, then I'll try to figure it out if I can. But yeah, you read about it, and if you have any doubt, then we can discuss it. I think meanwhile I can show you the week one. Okay, so if you really want to understand, then I think for 5 minutes we can go through some basic concepts. So it will help you to understand this week two lecture with less effort. Yeah. So let's move. Okay, let's move to the theory part. So, so this is the major earth structure. So we can segregate into primarily three layers. That is the core, the deepest one, then the mantle, the middle one, and the crust, the top one. So this is how the earth looks like. I think we all have seen this figure, and if we mainly talk about the crust part, because here we are more interested into the plate tectonics. So in the plate tectonics, the crust plays a major role because it form the plates. So under the crust part, we have mainly two crust. First is the continental crust and the oceanic crust. And if I like from this figure also, you can see that continental crust is more thicker than the oceanic crust, and the reason behind is that it has a less density as compared to the oceanic crust. So again, the concept that we have discussed just now, the isostasy. So to maintain the mass balance or to achieve that hydrostatic equilibrium, the depth of this continental crust has to be more as compared to the oceanic crust. So here also you can see that the thickness of oceanic crust varies from 10 to 70 kilometers, on contrary to oceanic crust, which has only 7 kilometer thickness. And that's why in this isostasy figure, like in the airy model, when we see it, we have a very thin oceanic crust. So that's the reason it has a very less thickness, I think. Admit. Hi Anmol. Are you are joining this course? So actually, the you know the time now of the course. So have you not received the reminders from the NPTEL team? Okay, okay. Think about the continental crust. So you can join from here, and from the next week onwards, you can start from the beginning of the session. So yes, I was discussing about the continental crust. So so yeah, continental crust has I think now my flow got interrupted. Okay, so yeah, continental. So in this figure, all of you can see that we have a more thickness of continental crust and the lesser thickness of the oceanic crust. That is marked with a blue box. And why there is a difference is because of the density contrast. So in general, the continental crust composition is silicates plus aluminium. That's why the short abbreviation for it is Cl, that is silicate plus, and Al represent aluminium. And for oceanic crust, we have a higher density composition, that is mainly Sima, which represent Si again for silicates, and Ma represent magnesium. So due to which there we can see the density contrast, and the general density of the continental crust is from 2.6 to 2.7 gram per cc meter cube, and for the oceanic crust we generally receive 2.8 gram per centimeter cube. So this is a continental part. Moving further, let's understand what is a lithosphere and the asthenosphere. So the lithosphere is the rigid surface shell that includes crust that we have discussed just now and the upper mantle part, and this complete lithosphere forms the plate about which we will talk. So these plates are the plates that involved in the plate tectonics. And so to make this movement happen smoothly, we need some agent that will provide the force for this plate to move. So for that, asthenosphere plays a role to facilitate that motion of the plates, and that's why it is in a like partial molten state. So on that the plate can easily float. And this diagram I think we have already seen. Now we can move, since we are behind the time, so that's why I'm moving a bit faster. So if I talk about the types of plate movement, so due to this forces, we can see mainly three type of movement. First is the divergent, where these two plates, that plate 1 and the plate 2, and here is the boundary of these two plates, so they are moving away from each other. So that's why we are saying that this motion is the divergent in nature. Now if we talk about another kind of movement is the convergent movement. So as its name suggests, here the two plates are converging. So this is the plate 1, this is the plate 2, and here they are the motion direction, and this is the boundary. So they are converging. And the third type of movement that we observed during this plate tectonics is the transform movement. So where they are just slide past to each other. So one plate is moving in the other direction and the second plate is moving in the upward direction. So this is the main three type of plate movement we see, and due to this plate movement we also see the landform on the earth's surface, because these are happening below the surface, so we don't experience these kind of movement. But when this, with the help of this landform, we can see that whether this is the divergent boundary or the convergent boundary. For example, if we talk about the Indian and Eurasian plate, so how we got to know that there is a convergent boundary? By analyzing their movement. So in this India and Eurasian plate, both plates are moving towards the direction of each other, and that's why we got the origincy of the Himalaya mountains. So Himalaya is the landform due to this convergent plate movement. So since we were discussing about the question of the week 1 assignment, where they were talking about the subduction. So to explain the subduction, I have gone through mainly the convergent boundary, because the answer lies in this convergent boundary. So under the convergent boundary, we can have a three kind of scenario. First is the continental collision, second is the continental oceanic collision, and the third is the oceanic and oceanic. So since we have a two kind of plate, continental and oceanic, so that's why we are getting three type of combinations. So let's understand first combination, that is continental collision. So in this figure you can see the first plate is again the continental crust, and the second plate is also a continental crust. Now the question comes like, which plate subducted and which plate will remain on the surface? So the plate which will have a higher density will be subducted under the plate which will having the lower density. So in this scenario we can say that the density of the row 1 would be higher than the density of the row 2. And due to this collision we see the mountain ranges on the surface. And the example of this mountain range is the Alps mountain range or the Himalayas mountain ranges that we see. Now moving to the second type of collision, that is the continental and oceanic collisions. So here we know that even we have discussed just now that oceanic crust is more denser as compared to the continental crust. So it's obvious that the continental crust will be subduct under the continental crust. And due to this kind of collision, what we will receive as the landform is the volcanic chains or volcanic mountain chain. And the famous example of this Andes mountain range or Mount St. Helens range. So since this oceanic crust has the water in it, so that water vaporizes and with the magma it comes as the volcanic eruption on the surface. Now to the last type of collision is the oceanic collision. So since both the plates are dense, we know, so again the oceanic crust which will have a higher density as compared to the other oceanic crust will get subducted under the oceanic crust which has a lesser density. And due to this kind of motion we form the trenches or the island ranges. For example, Japan is a island range. So here we can see the chain of the island or the volcanic island. And the very famous example is the Mariana Trench, which is the deepest part present in the globe. So I think this is the for the plate tectonic part. I hope it's clear to both of you. And now I'll stop here. So and yeah, I think I should stop, because if again I'll move into a different kind of questions, like there is a question related to earthquake. So it would take time to explain, and now we are a bit late. So wait.